Well, welcome to your first Chem 132 lecture narrated. And this is the way I present these slides. They come right from the book, except for some of the extra ones that I put in. And in all of the slides, if you look at the lower right-hand corner, it tells you what page it comes from in the Chem 132 class notes book. And of course, T is top, M is middle, and B is bottom. So we're starting with page 41 at the top. The whole topic of Chem 132 is really one thing, and that is chemical equilibrium. You may have had a lecture on equilibrium at the end of Chem 131, or your teacher may not have had time for it or whatever, but this is what the whole topic is going to be in the entire class. So I want to show you an example of a reaction here. Everybody has seen reactions like this last semester, and you know that these equations have several characteristics. First of all, the substances on the left are reactants because they're reacting together, and the ones on the right are called products because they're produced. These reactions must be balanced, so you have to have the same number of atoms of each type on each side, and the coefficient, for example, in front of the H2 can mean molecules, but usually it means moles. And there are also states of matter listed that are important in this class, especially gas, liquid, and solid. And the fourth one is aqueous, dissolved in water, AQ. If a chemist ran this reaction in the lab by starting with 1 mole of CO and 3 moles of H2, what the equation says is that they would react with each other to form 1 mole each of the products. And if you look at this, the moles do not add up because they're not supposed to. What adds up is the grams. The law is the law of the conservation of mass, and there has to be the same number of grams on each side because you cannot either produce or destroy matter in a chemical reaction. The type of a reaction where you start with all reactants and you end with all products is a one-way reaction, 100% to the right. But most chemical reactions are not like that. Most of them are what are called reversible. As soon as some of the products start to form, they can start to re-react and form reactants again. These reversible reactions have a terminology problem. If you were to write the reaction in reverse, you switch sides, could you now call the products the reactants if it was going in the other direction? And you probably could, but chemists have resolved that issue by saying, depending on how you write it, whatever's on the left is reactants and whatever's on the right is products, period. At the very beginning of the reaction, when there aren't any products yet, the rate of the reverse reaction would be 0 because there's nothing there to react. But as the reaction starts, the amounts of the reactants go down and the amounts of the products start to go up. As the reactants go down, their rate decreases in the forward direction, and as the products build up, the rate increases in the reverse direction, and eventually the forward rate equals the reverse rate. And that is the state called equilibrium, because you're making stuff just as fast as you're using it up, and it will not look like anything is changing. Whenever you have two opposite processes going at equal rates, that is what's called equilibrium in chemistry. And it's called dynamic equilibrium because things are not just sitting there. There's actually something going on, two processes in reverse directions. I just like this picture of equilibrium. You're putting it back just as fast as you're using it up. Because of the fact that the reaction's able to go in either direction, if the reaction is reversible, you don't end up with only products, you end up with a mixture of all four of the substances. Chemists have to know how much of each substance is left, not just that there is some of each, and therefore we need a mathematical way to calculate how much of each is left. In order to do that, chemists use what's called the equilibrium constant, or KEQ. What I'm going to do is first of all describe how these are written and what they mean. Then we'll talk about where it comes from. A KEQ is written as the amount of products at equilibrium on the top divided by reactants. And the EQ is a subscript for a general equilibrium constant. In the future classes, we're going to substitute different subscripts to describe what kind of a problem we're doing, but all of the K's have the same definitions as I show you today. These are general equilibriums. So for example, we're going to study Ka that has to do with acids, Kw is for water, Ksp is for insoluble salts, etc. But they are all KEQs. And one of the rules is that the amounts for gases are expressed as pressure in atm, which is what you studied in the gas laws, and for solutions, they're expressed as molarity, or moles per liter. This describes more detail about how equilibrium constants are written. The amounts of the products go on the top, and since these are all gases, I write it as pressure. The first symbol on the left of that fraction, PCH4, that's how I represent the pressure of CH4 in atmospheres. And you multiply by the pressure of water. And then on the bottom, it's the pressure of CO times the pressure of H2. And if there's a coefficient in front to balance, you also use it as a power. So it would be the pressure of H2 cubed. The question is, what does this mean? The equilibrium constant means that if you put any mixture of those four substances into a flask, they are not going to be usually at equilibrium, but they're going to shift to reach equilibrium. If you allow the reaction to come to equilibrium and measure the amounts of each of the substances left at equilibrium, and then plug in the amounts, you will get the same value of KEQ no matter what initial mixture you started with. You could start with all reactants, all products, or a mixture of all four. But when it comes to equilibrium, KEQ will always be the same number, and that's the reason why it's called a constant. How chemists discovered this is that this is not derived. This is a natural law. It's called the law of mass action. The thing is, a natural law in science is something that you can't really prove, but there's no known exceptions. It's like Newton's laws of motion, or the laws of thermodynamics, which we're going to study later in the course. You can drop 1,000,000 rocks and every single one of them will fall. That's the law of gravity. It doesn't mean you proved that the 1,000,001st rock will fall, but since you know that that's the way the universe works, people assume that it's true in every case. This is an actual experiment showing how the equilibrium constant works. Let's suppose that you were a chemist and you wanted to start with a reaction mixture that has 10 am of CO and 30 atm of H2. Now we're going to assume that chemists know how to put this in a flask at those amounts. That's analytical chemistry. We don't want to study that, but we're going to say that if you do that, and then you let the reaction come to equilibrium, you can measure all four of the amounts of the substances at equilibrium. And those are shown below the first line. Those are not calculated. Those are something that someone would have measured in the lab. Now, if you plug in those amounts into the equilibrium constant expression, particularly cubing, the 18.3, you will get a number that's called the equilibrium constant, the value. And the thing about this is everybody's always concerned about significant figures. In this class, you don't really have to worry about it very much. But what's important is that you get the correct answer both by calculating and also making sure that you know about a concept called round-off error. So that's what I want to talk about in the next couple of slides. I don't care if you write this as either in scientific notation or as a decimal. I just want you to be able to go back and forth between the two. If you know that it's 4.1 times 10 to the minus 4, I want you to also know that that's the same as 0.00041, because your tests are multiple choice, and all you have to do is recognize the answer in whatever form I put it. Now, one problem with getting that correct answer, though, is calculator use is probably at least half of this class to be able to know how to use a calculator correctly. It's very easy to get the wrong answer on a calculator if you don't enter it correctly. And this is one of the classic mistakes. So let me show you this. If you take that fraction and try to evaluate it, you're supposed to theoretically take the 3.9 times 3.9 and put it on the top, and the 6.1 times 18.3 cubed and put that on the bottom, and then divide. That's the correct answer. The problem is that many students will enter this on a calculator as just 3.9 divided by 6.1, 18.3 cubed. It looks correct, but it is not. If you do this on your calculator, the calculator is not going to divide by 18.3 cubed. It's just going to do the next calculation and it's going to multiply by it. And you get the completely wrong answer. In order to make absolutely certain that you get the correct answer when you're doing a fraction, you always have to put the entire denominator in parentheses. Otherwise, the calculator will not divide by both numbers. If you put the denominator in parentheses, you get the correct answer. The first time you do this and forget the parentheses, it will be a shock because you'll get an answer that doesn't look anything like what I say it is in the homework. I don't care how many significant figures you express an answer to, but it's very important that you do the right thing with significant figures during the problem. The concept is that you do not want to chop numbers before the end of the problem. If you look at that expression that we just did, let's suppose that you rounded those numbers before you did the problem. So you made the 3.9s 4s, and on the bottom you had 6 and 18 cubed. Let's forget about these decimals. Well, you get a pretty different number. I mean, if your answer was 4.57 and the answer I had on a test was 4.1, I wouldn't be very confident that it was the right answer. And if you didn't even round, if instead of rounding you just chopped the decimals on the 3's, Look at that number. It isn't even close. It's a completely different number. So this is the rule. You can show in math and computer science that if you keep at least 3 significant figures in each number when you're calculating, you'll do pretty well as far as the round off error. 4 is better and 5 is almost perfect. The rule is just do not chop or round numbers while you're doing the problem. Keep it in the calculator and do not round until the very end, and then you'll be safe. Now let me show you another experiment. In the first one, we started with 10 ATM and 30 ATM. I want to do another experiment now. Let's suppose the chemist cleaned out the flask and started with different amounts this time, 20 and 50, and let them come to equilibrium. So those are what are left according to the chart. Since you started with different amounts, you started with more at the beginning, I don't think it would surprise anybody that you would end up with different amounts at the end from when you did the first problem, because there's just more stuff there. But when you plug in the numbers at equilibrium, you get the very same value of KEQ. That's why it's called a constant. Now the thing is, though, 4.0 and 4.1 are not exactly the same answer. That's another thing we have to talk about. Your answers will sometimes be slightly off, either from rounding or from the fact that we're dealing with experimental error in this class. Those are the same number within experimental error. If your answer differs from mine in maybe the third significant figure or something, you just have to get used to it. It probably means that we just rounded differently or something. It doesn't mean you're wrong. You'll get used to recognizing when your answer is actually correct. I never put the answers close enough together on a test that you will ever get it wrong by just using rounding wrong or something. You'll always be able to recognize the answers. Now in this third experiment, the chemist is doing something different again. Instead of starting with reactants, he's starting with products only. Normally, if this reaction was one way, you couldn't do this because the reaction is over once you get to the products. But in this case, since the reaction is reversible, it goes in both directions, and you can do this. And so when the person let it come to equilibrium, plugged in the equilibrium numbers, he again got the same value of KEQ. So the thing is, this is what KEQ means again. No matter what initial mixture you start with, you get the same value of KEQ when you come to equilibrium. That means that the simplest kind of a problem I can give you related to the equilibrium constant is just a plug-in. Let's suppose that I gave you that reaction that was balanced at the top of the page, and I give you the pressures of the gases at equilibrium. Now, there's two things here. I said the temperature, and normally I wouldn't do that because I made up my mind that in these problems I do not give you extraneous data. If there's something that does not affect the answer to the problem, I try not to give it to you because these are confusing enough if you only get the data you need. And the other thing is that I try to teach these problems by using key words. A lot of the trouble in 132 is that students don't know what kind of a problem to do when they read it. The key words in this problem are at equilibrium. That means we are at the end. It doesn't matter what we start with, because the question is, what is the value of KEQ? And KEQ has the same value no matter what you start with. And so therefore, all we're going to do is we want to write the KEQ expression and plug in those numbers. Here's a flask that shows what's going on. So at equilibrium, those are the three numbers that are balanced, and You just want to plug them in order to get the KEQ. So I wrote what's called the KEQ expression. It's the mathematical expression. And you have the H2 is cubed and the NH3 is squared because they have a coefficient in front. And when you plug in the numbers, you then calculate it on your calculator. Now, the number on your calculator is probably going to have more decimal places. I just rounded it to 3.58. You could round it to 3.6 times 10 to the fourth, or you could write it as 35,800. It's the same number. I don't really care as long as you recognize the answer. Now, the second problem we're going to do takes a little bit more work because in problem 1, I gave you the amounts of all three substances at equilibrium. But problem 2 is one that's very similar to one we're going to do all semester long. Chemists a lot of times do not design the experiment so that they can measure everything at equilibrium, because that is a very hard problem to do. You have to remove a sample, separate the three things, measure them separately from each other. It takes a long time. The way these experiments are usually designed is that a chemist will only measure one of the substances at equilibrium. But if you have a balanced equation, you can calculate the amounts of the other ones by math before you plug into the equilibrium expression to find out what is KEQ. So I gave you a reaction down below where we're starting with 8 ATM of the reactant and none of the products. When I give a problem like this, I'll usually give you that initial row because people sometimes have a hard time translating the words into what is actually there in the problem. And the question says if the pressure of H2 gas is measured as 0.89 at equilibrium, what are the other pressures and what's the value of KEQ? You can recognize that it's this kind of a problem because I don't give you everything at equilibrium. I give you only one thing and then ask you for the KEQ. The thing about this is that when you do this kind of a problem, we don't know what the value of everything is, and so you are going to have to use an X in the problem in order to solve for it. This is what it looks like in a flask. We're going to start with 8 ATM. At equilibrium, I gave you the concentration of H2, but we don't know the other two. Whenever you have to introduce a variable into an equilibrium problem, you're going to use what I call an ICE table, which I show on the next page. I copied the initial concentrations, as you can see here. The thing is that you know that this reaction is not at equilibrium yet, because at equilibrium you have to have a mixture of everything, and the products have a concentration of 0. So you're going to have to do what's called in chemistry shifting to the right. You always shift towards the zeros because the amount of the zeros has to go up and the amount of the HI has to go down. So the next row I make is a change row. I'm going to let X equal the amount of H2 that forms. And since you get one I2 for every one H2, both of them are going to be plus X. You're going to end up with the same amount. Now the question is, where did those two come from? They came from the breakdown of HI. It's the only other thing in the problem. In order to make one H2, you have to break down two HIs. And that's the reason why we're using a negative 2x. If there's a coefficient in front of the substance, you can also put it in front of the x. And you will never have plus and minus x's on the same side. The pluses are on one side and the negative is on the other. This shows you visually why you have to use up two HIs in order to get one H2 and one I2, because you have to have one H from each one. So you lose 2 when you make one H2. So when you get to the equilibrium, then it will be what you started with plus how you changed, 8 minus 2x for each I and x for each of the products. Because those three words at the left start with the letters ICE, you can call it an ice table. Some people call it an ice box, but nobody knows what an ice box is anymore, so I call it an ice table. And the problem tells you that the pressure of H2 at equilibrium is 0.89 atmospheres. So that means that will give you X. Since you now know what X is, you can plug it into each of the other substances and it will tell you what the final concentrations of each thing are. Then you can write the equilibrium constant expression, plug in those numbers, and you will get an equilibrium constant. I don't care if you write it 2.0 times 10 to the minus 2 or leave off the 0 or write it 0.02, as long as you recognize the answer. Now this is another problem of this type, but it looks more complicated, but it isn't. It's just more substances. So I give you the initial row where you're starting with 4 Cl2 and 9 H2O. And what I ask is that the pressure of O2 is 0.659 at equilibrium. So I want you to calculate the other substances and the value of KEQ. And because you're only getting one thing at equilibrium, you know that you're going to have to use an ice table. So that below shows the first row. Now, the thing is, you know that you always have to shift towards the zeros, and so the pluses always go on the side with the zeros. The minuses always go on the other side. If the zeros were on the left, then you would put the pluses on the left, but I don't usually do that because it's confusing. So I usually have the zeros on the right. So you're gaining the stuff on the right, so it's pluses, minuses on the left, and then if there's a coefficient in front of the substance, you also put it in front of the X. So you end up with the beginning minus the change. Now, the thing is, I could give you, instead of giving you the 0.659, which is O2, and that gives you X at the end, I could have given you, for example, the concentration of, the final pressure of water vapor, but then you would have to set 9 minus 2x equal to that and solve for x. But I don't do that in any of the problems because we don't do it at any of the problems we do during the semester. We can always get 1x. And so I figure, why make it any harder than you need to? I limit the difficulty to what we're actually going to do. So since we know what the pressure of O2 actually is then, because it's given, that is also equal to x. And so we can plug in x for all the others. After you then calculate each thing at equilibrium, you can get the KEQ. I plugged in each of the final values, but now please remember the fact that you absolutely, if you're doing it on a calculator, all in a string, you have to put the denominator in parentheses. If I were you, I would try it without doing that and see what answer you get. But if you do put it in parentheses on the bottom, you'll get the answer in the next slide. So when you plug into the equilibrium expression, that is the number you would get if it is correct. I would experiment on your calculator. Try putting this in without putting the two values on the bottom in parentheses and see what you get. Unless you put the denominator in parentheses, you will get a completely different number than what it's supposed to be. This is a third kind of problem that we want to do. And in this problem, I'm not going to give you any of the substances at equilibrium. I'm going to give you the equilibrium constant. If you look at that equation at the top of this page, it's given that the equilibrium constant is 79.7. The reason they have so much data on this reaction is that the reverse of this reaction is probably the most run chemical reaction on Earth, because SO2 plus O2 requires a catalyst and heat, and if you make SO3 dissolves in water to form sulfuric acid, H2SO4. And H2SO4 is made and exported by countries more than twice as much of the second place candidate. And so this reaction has a lot of data that people have gathered over the years. And this tells you that the equilibrium constant is 79.7. Then what I'm asking in the question is, suppose that a chemist mixes together the three amounts that you're given there. The question is the reaction at equilibrium? And you can tell not only that, but you can tell which way will the reaction need to shift to reach equilibrium. So in order to be able to visualize this, I showed you a flask that has those three initial amounts in it. And of course, if this reaction is at equilibrium already, if you plug those three numbers into the equilibrium expression, you should get 79.7. So that's what I did. I took the equilibrium expression and plugged in those three given numbers. And I ended up with 12,000, which is obviously not 79.7. And so that means this reaction is not at equilibrium. When I plugged in the initial values, though, you can see that the expression that I plugged into is the same one as for KEQ. But you can't call it KEQ because these are not at equilibrium. Chemists use the letter Q to stand for the number you get when you use the equilibrium expression, but you plug in initial concentrations. The reason why they call it the reaction quotient is that a quotient is a division problem in math. So if the Q is not equal to KEQ, you know that the reaction is not at equilibrium. But it's also significant that the Q is greater than KEQ, because that tells you which way the reaction will shift to reach equilibrium, as I show on the next slide. If you want to make that Q value, which is too large, go back down to 79.7, you're going to have to change the top and the bottom of the fraction. The question is, how do you make a fraction smaller? Well, in math, you can either make the numerator a smaller number, or you can make the denominator a bigger number. If you do that for this particular one, what's on the top of the fraction is products, and on the bottom is always reactants. So if you want the number 12,000 to go down and reach equilibrium, you're going to have to decrease the products on the top and increase the reactants on the bottom. In a chemical reaction, since the reactants are on the left, you are going to have to do what's called shifting to the left. And what that means is you're going to have to take some of the products from the right-hand side and shift them to the left. That way the products will decrease, the reactants will increase, and you'll be able to stop when the reaction reaches equilibrium. So that tells you that whenever you calculate Q and it comes out greater than KEQ, you'll always have to shift to the left to reach equilibrium. Now in this problem, I said, let's clean out the flask and try a new set of concentrations. So in this experiment, the chemist is mixing the three amounts that I give you at the top of this page, and it's the same two questions. If you plug in for the Q value, you get 0.071, which is obviously less than the KEQ value, 79.7. And so this time, you're going to have to make the products on the top increase to make the fraction larger, and the reactants on the bottom to decrease. And that is what's called, in chemistry, shifting to the right. You're taking some of the reactants so that they go down and converting them to products so that the products go up, and it stops when the reaction reaches equilibrium. So whenever Q is less than KEQ, you shift to the right. I summarize this in the table at the bottom of this page, or in this little square box, because we're going to use this over and over again in different lectures in the class. That whenever Q is greater than K, you shift to the left. If Q is less than K, you shift to the right. The thing is that you can remember this. This is kind of a cheat technique. You can remember this because you shift the opposite direction of how the greater than sign actually points. Now, one of the things we have to do is make sure that everybody understands the difference between Q and KEQ, because we compare all the time the Q, which is the initial values, to the KEQ, which are the equilibrium values. Q and KEQ have the same mathematical expression, but if you look at it, Q can have many different values for the same equation, because you can make any initial reaction mixture you wish. You can choose any concentrations you want and mix them. On the other hand, no matter what concentrations you start with, you can have many Qs, but at the end, when you reach equilibrium, if you plug the numbers in, KEQ has only one value. That's why it's called the equilibrium constant. So no matter what kind of a mixture you start with, there's only one KEQ for each reaction. So what you're really doing is you are comparing the initial to the equilibrium when you compare Q and K. And that is what tells you which direction the reaction shifts. There could be one problem with calculating a Q if there happens to be a 0 for the initial concentration on the left of the equation, because then if you try to put the reactants on the bottom, you would have to divide by 0, which you can't do. But you never have to do that, because if you have a 0 either on one side or the other, you already know before you start that you have to shift towards the 0, so you don't need a Q value. Now this is something that you wouldn't know unless I just told you, and so this is a convention that chemists have adopted, and what it is that you're only supposed to put into an equilibrium expression things that can change easily. The thing is, solids and liquids have basically a constant concentration. They change very little, either from heating or compressing or any other change. And so chemists do not put solids and liquids into the equilibrium expression. On the other hand, gases are very easy to change the concentration of. Whenever you put air in your tires, for example, you changed the concentration of the gas, and that's an easy thing to do. It's also easy to change the concentration of aqueous solutions. If you wanted to change the concentration of salt water, for example, all you have to do is dump in more salt or boil away some of the water and it will get more concentrated. So you only put gases and aqueous into equilibrium expressions. I showed you an example at the bottom of the page where you have both solids and gases. And if you look at the equilibrium expression, it does not have the solids included. It doesn't mean that the concentration of the solids disappeared. What it means is that since they're constant, chemists consider that those numbers are already incorporated into the KEQ value. And here I showed one where we're using aqueous. When you are expressing the concentration of something that's aqueous rather than a gas, you're going to express the concentration of aqueous solutions as molar. And the way you indicate molar in an equilibrium constant is that you put square brackets around the substance in solution. And so if you look at this equilibrium expression, I have the products on the top in square brackets. I have NH3 aqueous on the bottom, but I did not include liquid water because it's a liquid, and we have liquid water many times in our expressions, and liquid water just doesn't go in. Now here's a reaction where you have a solid on the right, and so if you put products over reactants, there wouldn't be anything on the top because you don't put solids in. Obviously, there has to be a number on the top, so you could think of solids and liquids as being replaced with a 1. Now this is a review of molarity. And this is all the way on page 137 in the book because we're going to talk about it again later in the class. But the thing is, I want to make sure that everybody knows what molarity is and how to calculate it because we're going to use it so frequently all throughout the semester. If you remember from Chem 131, the definition of molarity is you take the number of moles of what's dissolved divided by the number of liters of solution. You can't plug in grams and you can't plug in milliliters. You have to convert them first. And if you rearrange the equation mathematically, you can solve the equation for moles and convert it to grams, or you can solve the equation for liters and convert it to ml. We're going to use all three of these forms at different times in the class, but I want to do a molarity calculation question just to review a little bit 131. This question asks, what's the molarity if you dissolve a certain number of grams of aluminum sulfate and you dissolve it in enough water to make 750 ml of solution? And now, if you remember what molar mass is, that is when you look up the weight of each element in the periodic table, multiply by the number of atoms there are, and then add them. So if you were going to calculate the molar mass of aluminum sulfate, you have to count the atoms right because that's a frequent place where students make a mistake. There's 2 aluminum, and please notice that there are 3 sulfur because there's a 3 outside the parenthesis. And oxygen, there are 12 oxygens because it's multiplied 3 times 4. If you add all of those weights, you get the molar mass listed there. In order to plug in for molarity, you have to convert the grams to moles by dividing by the molar mass, and you have to convert the milliliters to liters by dividing by 1,000. And if you plug those numbers in, you get 0.0285 moles per liter, which chemists usually write with a capital M for molar. Now, we've already done 3 kinds of problems. In the first kind, I gave you all the substances at equilibrium. In the second problem, I only gave you one of the substances, and you had to calculate all the others. In the third problem, I didn't give you any of the substances at equilibrium. What I gave you was the equilibrium constant, and we compare Q to that. In this problem, I'm not going to give you any numbers at all, because all this one is just which way will a reaction shift if you make a change. This principle is called Le Chatelier's principle, and what it is that if you have a reaction that's already at equilibrium and you change the conditions, you are going to get a shift in the equilibrium in such a way that it relieves the stress that you put on the reaction. We're only going to use one of the three principles that Le Chatelier's principle deals with. You can change the temperature, the pressure, or the concentrations. We're only going to change the concentrations. For example, if you have a reaction that's at equilibrium and you remove something from either side, the equation is not at equilibrium anymore. You have to shift toward what you removed in order to restore the equilibrium. If you add something, though, to one side or the other, you have to shift away from what you added in order to use up the extra that you put in. I tried to show this with the analogy of a seesaw. If you start with a balanced seesaw that has 3 of those blue balls on each side, if you remove 2 of them from one side, the seesaw is going to be weighted on the other side and it goes down. In order to get it back to equal, you have to shift toward what you removed in order to get it to balance again. If, on the other hand, you start with 2 balls on each side and you add 2 more to one side, that side is going to go down. But in order to get back to equilibrium, then you're going to have to shift away from what you added in order to restore the balance again. The problems, when they're asked in words, look really complicated, but they're not really that bad. If you look at this equation at equilibrium that I wrote on this page, it says that in number 1, if some of the CO gas is removed, you will shift to the left because you have to replace what you removed. If you remove some of the CH4 from the right, you'll shift to the right. You always shift toward what you remove. If you add some H2, you shift to the right again because you have to use up what you added. If you add water vapor to the mixture, you'll shift to the left because, again, you have to use up what you added. Now, all of those equilibrium principles are something that we use both in class and in lab. The thing about it is we have to move into another topic at this point because we have to discuss what kinds of things inorganic chemists study, because we're studying inorganic chemistry. The truth of it is everything in the universe is only made of one of 2 things from the perspective of chemistry. Matter has to be either a pure element, which is just one thing by itself, can't be broken down anymore, or a pure compound, and that is a combination of 2 or more different elements. A mixture is also something they talk about, but all that is mixing together elements and compounds to make a mixture physically. It's not really a new substance. So what we want to do is the vast majority of things we study in this class are actually compounds. So we want to get into a discussion of the 2 different kinds of compounds there are and which one we're going to study the most. There's actually 2 kinds of compounds you can identify. One is called covalent and the other one is ionic. If you remember what a covalent compound is, these are ones that contain molecules like H2O and CO2. The atoms in the molecules are held together by covalent bonds. And if you remember, covalent bonds are made of shared electrons. Electrons still have to go in pairs, but they can be shared between atoms. Covalent compounds don't have an electrical charge because the electrons are being shared, not transferred. And so theoretically, if you had a beaker of water, for example, you could pick up a molecule that actually contained one oxygen and two hydrogens bonded, and it would be separate from all the other molecules in the liquid. I like to say that covalent compounds are actually Peppa Pig compounds because they use the very suspicious technique of let's all share. The other kind of compound you find is what's called ionic. And ionic compounds form when you get a transfer of electrons from one atom to another. The electrons are not shared anymore. They're actually completely transferred. And when you get an ionic compound, it does not have any molecules because the smallest unit is an ion. It's just alternating ions. You can't pick out one individual unit. And I'm going to show you a picture of a crystal of an ionic compound so you can see that. Because the ions are charged, they're held together by positive to negative attractions, which are called electrostatic or electroweak forces. And of course, there are charges then in these kind of compounds. The thing is that the overall compound is neutral because the number of positive charges has to equal the number of negative charges, and that has a lot to do with how you write formulas, which we're going to look at later. The thing about this is that the two kinds of ions that exist, of course, are positive and negative. Positive ions are called cations. That is a word we're going to use a lot during the course of the semester. They're not called cations. That's one of those boys from down Louisiana that take that stomp, hit an alligator on the head with that stomp. They pull a pea road down there by you, use that fruit jar, that jambalaya, etouffee. That's a cation. These are cations. The negative ions are not called anions. That's what you put in a salad that makes your breath smell bad. Anions is what negatives are called. And anytime you want to write the formula for an ionic compound, the rule is that you always put the positive ion first. And almost always, positive ions are metals. Metals don't want to gain electrons. They only want to lose them. The other ion that you're going to become very familiar with after several lectures is ammonium. NH4 plus is not a metal, but it's what's called a polyatomic ion that has a positive charge throughout the whole ion. And it acts like a metal, so anything that has ammonium in it is also ionic. We use a lot of ammonium compounds in chemistry all the time, so it's a very important ion to pay attention to. The negative ion we're going to look at is going to be either a nonmetal that has gained electrons or one of those ions that's called a polyatomic ion, and you always write the negative ion second. One of the very simple things that I ask is which compounds are ionic and which ones are covalent. So how do you know? I'm going to use a rule that's 97% accurate at the beginning of this class. I'm estimating that About 3% of metal compounds can actually be covalent. But for this part of the class, I'm going to say that you can be safe to classify any compound that contains either a metal or ammonium as ionic. If the compound does not contain any metal, it's all nonmetals and metalloids. Those kind of compounds are covalent. We're going to study mostly ionic compounds because in Chem 132, we mainly study ions in solution, and you'll see what that's about. Covalent compounds, many of them, not all of them, are organic. You're going to have a lot more to say about covalent compounds next semester if you take organic chemistry. Of course, the question is, where on the periodic table do you find the metals? Well, I think everybody probably remembers from 131 that if you look at that black slash line on the right of the table, everything to the left of that line is actually a metal. And everything to the right of that line is a nonmetal. The only exception is that there are the ones along the slash are called metalloids. There's only one of them that's not called a metalloid, and that is aluminum. Everybody knows, I'm sure, that aluminum is a metal. If you take a aluminum ladder out to the middle of a cornfield during a thunderstorm, you climb the ladder, juice up your finger, stick it in your mouth, and then hold it up, I guarantee you, you are a lightning rod. The electricity will hit your finger very well, and the aluminum conducts electrons. So aluminum is definitely a metal. The reason why ionic compounds do not have molecules is that all they are is alternating ions. If you look at a crystal, for example, of sodium chloride, each sodium is surrounded by 6 chlorides, and each chloride is surrounded by 6 sodiums. You can't pick out just an individual unit of NaCl, so ionic compounds don't actually have molecules. And this slide shows what kind of ions you can have in ionic compounds. There's 2 different kinds. One is called monatomic, and these are individual atoms that have either gained or lost electrons. So this would be like Na plus or Cl minus. The other kind of ion is what's called a polyatomic ion, and those ions act together as a group, and the entire group has a charge. Those are things like NO3 minus, nitrate, and PO4 3 minus, phosphate. I want you to know some of the ions that are used in chemistry. Now, since this class is online, obviously you're going to be able to look these up, but I certainly want you to at least be able to look them up to the point where you can find what you need when we name a compound. So I'm going to talk about this as if it was not online. If you were in a class, this is what I would want you to know, but you have to realize the fact that you're going to be able to look at your book when you're taking tests. I still want you to be very familiar with these for both lab and class. The ions that I would ask you to know normally are listed in this list. Now, a list is a very bad way to learn ions, because then it's just plain memory, but there's a lot of principles you can do that show you better ways. But I did list the ions that I would normally want you to know according to, first of all, +1, and then here's ions that are +2, And here's ions that are +3 and +4. So these are the positives that I would normally ask, and we're going to talk about naming these in a second. The negative ions that you are supposed to know are, first of all, monatomic ions. Those are the ones on the left of this chart. The polyatomic ions are the ones that have more than one atom that have, and the group has a charge. And if you look at these usually end in either ITE or ATE, and I'm going to explain that when we talk about naming. And this table lists -2 and -3 ions, and on the right again are the polyatomic ions that have those charges. Now, by far the best way to know these is not by a list. If you look at this periodic table on page 52, these are the ions that I would ask normally for people to know the charges of, and the names. You probably know most of them already. You wouldn't have to know the ones in the blank squares. I would only want you to know the ones that are listed as having something in the box, because those are important ones. Now, if you were going to learn these, it's not that difficult in one way, because you already know the principle that group 1 ions always have a charge of +1. Hydrogen is not really in group 1. It's really a separate ion by itself because it's a nonmetal. But all of the ones in group 1 are +1. The ones in group 2 are +2. The ones in group 3 are +3. And coming from the other direction, noble gases, that's group 8, have no charge because they don't really make ionic compounds. 7, or the halogens, are -1, and 6, or the chalcogens, are -2, and 5 are -3. And down at the bottom of those columns are some positive ones, but we're talking about the top when we're doing negative charges. Now, if you look at the ones in the middle, the transition elements are the primary ones that can have more than one charge. If you look at the top row of the transitions, there's 3 blank spaces, and then 24, 25, 26, and 27 can all be either +2 or +3. 29, copper, is the one that can be 1 or 2, and that's the one that's different, so people usually try to remember that. There's several of them that I listed as only having one charge, nickel and zinc and cadmium, etc. And a couple of the ones at the bottom of the groups below the black slashed line can have more than one charge. I normally tell people, if you were going to memorize these, the way to do it is to take a blank table like this. And you don't even try to figure out what the name of each thing is or what symbol to put in. All you have to do first is figure out what charge goes in what square. If you know that, you can look at a periodic table when you're doing problems, and that will allow you to look it up and know what the charges are. So this is the suggestion for being familiar with positive ions and negative ions that are called monatomic. I want to talk about how to name these ions, and we're going to do the positive ones first. The thing about this is that on the first exam, I'm going to have 20% of the questions, which is 10 out of 50, are going to be naming. And the first type is that I'm just going to give you like the formula of an ion and ask you for the name. So SO42-, I'll give you 5 choices and you pick sulfate. Or I'll give you a name, for example, chromate. I'll write the name out, and then I'll give you 5 formulas, and you're supposed to pick CrO42-. The third kind of a question is that I'm going to give you a complete name, like aluminum sulfate, you are supposed to write the two ions down, cross, as I'm going to show you using the cross method, and then write the final formula on the test. Now, as I told you, you're going to be able to look up the names of the ions, so I'm going to emphasize writing formulas where you have to put both ions in cross, but I still am going to ask names and formulas of individual ions, and that's 20%, and we won't have any naming after that in the course. I'm just going to assume that you know the names of the common ions and just use them routinely. But now I want to show you first of all that if you're naming positive ions, the ones that can only have one charge, the ion gets the same name as the element. So for example, K plus is potassium ion, Ca2 plus calcium ion. The time when there's a little bit of difference in the naming is when the ion can have more than one charge. In the transition elements, where you can have more than one charge, the most common system is to use a Roman numeral in parentheses after the name in order to tell the charge of the ion. And this is what's called the stock system. You can use this system for any of the ions that have more than one charge. So, for example, iron 2 is the 2 plus, iron 3 is the 3 plus. Now the thing is, I only want you to know 3 ions by an older system, and the reason I'm doing this is because medicine has not switched. Medicine, in large part, doesn't usually adapt to the rules of naming that are produced by the World Committee of Chemists, which is called the IUPAC, we're going to talk about later. The thing is, usually they keep calling things the same thing they called them since the 1880s. Anyway, the one system, I want you to know 3 ions by this. The older system used the Latin name of the element followed by the suffix OUS for the smaller of the 2 charges, and IC for the larger charge. So by that system, iron 2 could also be called ferrous ion. Iron 3 could also be called ferric. And there's also for copper, a cuprous and a cupric. For example, the drug that you take as treatment for anemia, when you take iron pills, the form that they call it, the generic name, is actually ferrous sulfate. They do not call it iron 2 sulfate. Medicine usually sticks to older patterns, and so I wanted you to be familiar with this for just 3 ions. The third one that I want you to be familiar with by this system is mercury. Mercury is by far the most important environmental toxin there is, because there's just so much of it in nature, and I think it probably always will be. So people have studied it in detail. Now, if you look at mercury 2, which is also called mercuric, it's not the Latin name this time, but I guess it's Latin anyway, because mercury kind of is Latin, so it's mercuric. The +2 ion is exactly what you expect. It's one mercury that has lost 2 electrons. The thing you need to know that's different is mercury 1, or mercurous ion, always goes in pairs. It's always 2 mercury 1s that are covalently connected. This was discovered in the 1980s, and they reported it in the Journal of Chemical Education. Coincidence? But anyway, I showed a picture of it. The 2 Hg pluses are connected, since they always go as a pair, you can't reduce the 2 on the Hg2, and the two of them together are plus 2 because each one is plus 1. The other positive ion that you absolutely have to be familiar with is really the only one that you would call a polyatomic ion without a metal in it, and that is ammonium. The compound ammonia is one of the two common names that I want you to know in Chem 132. Certainly everybody knows H2O is water. You don't call it any other name. And nobody calls NH3 anything but ammonia. And that is neutral. If you put a plus from an acid, an H plus, onto it, you get ammonium ion, and that is an ion that makes everything ionic if it's in it. And we're going to show lots of that when we do acid-base chemistry in the next couple days. As for the naming of the negative ions, there are 3 different endings that are used, and this is always confusing to students, so I want to show you carefully what those endings are. The first one is IDE, IDE. This is the ending that they use if the negative ion is monatomic. In other words, it's just one single atom with a negative charge. So you have things like chloride, Cl minus, and oxide, O2 minus. There's really only 8 of these that I want you to remember. If you look at the periodic table on 52, on the upper right, there are 8 negative ions listed, and those are the ones that end in IDE. So you have fluoride, chloride, phosphide, and those are the ones that are IDE ions. The polyatomic ions that are negative end in 2 different suffixes, ATE and ITE. The problem with this is trying to remember which is which. The thing is, those 2 prefixes indicate that oxygen is present. If you think of ITE and ATE as meaning that oxygen is connected with another element, that's when you use those. The problem is knowing for each element which one is the 8, because ATE can mean either 4 oxygens or 3 oxygens, depending on the ion. I showed you first of all the example of nitrate. NO3 happens to be the one that they call the 8. There is no NO4. And the other ion, nitrite, whenever you know what the 8 is, the ite always has exactly 1 less oxygen. And the 2 ions have the same charge. So if you look at the other 2, sulfate, the 8 for sulfur is 4. It's -2, so that means automatically you know that SO3 is sulfite. 1 less oxygen, same charge. There aren't very many of these that you actually have to remember what the 8 is. There's maybe 6 or 7, I haven't counted them. And sometimes there is no ite. For example, for carbonate, CO3, there is no CO2 carbonite, at least that we're going to study. And so, but this is the ones that end in ATE and ITE. Now, because of the importance of this chlorine series, there are actually 4 ions that have chlorine connected to oxygen. So you have to come up with a name for each one of these. There is an 8, which is ClO3, and there is an ite, which is ClO2. But there's a very important ion, ClO-, which is Clorox bleach, sodium or potassium hypochlorite, guess it's sodium is the bleach. And there's another one, perchlorate, which is also very important. It's the basis of the explosive industry, among other things. So the way they named ClO minus is that since chlorite has two oxygens, the prefix hypo in medicine means too little. For example, I'm hypothyroid. I don't have enough thyroid hormone, so I have to take a supplement each day. So since it has one less oxygen than the ite, they call it hypochlorite. The one that has one more oxygen than 8, instead of using the prefix hyper, which usually means too much, they just use per, so that is perchlorate. The elements bromine and iodine have the same series of atoms, or the same series of ions, except that instead of chlor, you use bromo or iodo. So there's a bromite and an iodite. One of these ions you're going to see that's very important again in organic is the ion IO4 minus. It's called periodate. This one is one of the major oxidizing agents in organic. I only want you to know the chlorine ones, so that I just want you to be familiar with these names and charges. There's a couple of ions that I want to point out separately. OH minus, of course, is the ion that makes a base solution. If you have a solution of OH minus, the pH is above 7 and it's basic. So the thing is, this ion should really be called hydroxite because it's an element combined with oxygen, but nobody's ever going to call it that because it's been called hydroxide probably since the 1800s. So the thing is, it's just a name that we're stuck with. That one won't ever change. There's also a very important negative ion that if you look at the formula O2 minus, that is the ion oxide. It's oxygen with a -2 charge. But there is an ion that has one more oxygen than oxide, so they use the prefix per. O2, 2 minus, is peroxide. And so it follows that rule about using per, but the thing is, that ion always goes in pairs. You have to have O2, 2 minus. You can't reduce the O2. And the thing about this is we use this, especially if we're doing qualitative analysis, which we're not really doing in lab this semester too much. But the thing is that this is a very important ion in the lab, and it's also very important in physiology, which I will probably mention later what peroxide has to do with it. You're going to see peroxide again both in this class and in organic, and so I definitely wanted to use that as one and make you aware of it. The other one that I want you to remember is cyanide. As you know, this is an important one in biology. It's a deadly toxin. They used to use it in the gas chamber for executions, and it ends in IDE probably because there's no oxygen, and it's actually a carbon and a nitrogen together, covalently bonded with a negative charge, and it's a single ion, so they call it cyanide. The next thing I want to review is how you write formulas for ionic compounds if you know what two ions are going to come together. Now this is a method that you can use that's called the cross method, and I don't know how your teacher showed you this in 131. Sometimes they use an algebraic method, but I want to do things very fast, and so the cross method is a quick way to do things. I'm not going to show you the method by going through these steps. These steps are the way you do it, but I want to do it by using examples, so let's look at an example. Now we're going to try to write the formula for aluminum chromate. And when you do this, the metal ion always comes first. And so we're going to put down Al, and you know that it's a +3 because it's in group 3 in the periodic table. Now the other ion, chromate, we're going to put in parentheses. This one is a memory ion. The chromium-8 has 4 oxygens, and it's a -2 charge. So what you do in order to do the cross method, you take the number and not the plus or minus, and you cross it onto the other atom. And when you're done, you cross out the charges. And so the final formula is circled. You can't change the CrO4 to anything else because it is actually 3 groups of CrO4. And I want to show you that this does actually give you a neutral compound. If you draw what this actually is, it's actually 2 + 3 aluminums, which is +6, and 3 groups of -2 chromate, which is -6. The cross method will always give you a neutral compound if you do it correctly. Now here I want to do 2 compounds that sound very similar on the surface, but they are very different actually. I want to write the formula for iron 2 sulfate and iron 3 sulfate. The iron 2, as we said, is also called ferrous, and the iron 3 is also called ferric. The way you would write these formulas first is that you would write the metal first. So we have in the top one, iron is +2, which comes from the Roman numeral, and sulfate is SO4 with a -2 charge. So when you cross them, you end up with a 2 on each ion. Since ionic compounds do not have any molecules, the way you want to write the final formula is if you can reduce the 2 subscripts, you do. And so since you can divide by 2 each one, you're actually going to write FeSO4. And we do not write ones after, we don't write ones. And if there's a 1 after, we also don't write the parenthesis. So the correct formula is just FeSO4. If it's iron 3 sulfate, the iron is +3. So when you cross it down, you end up with 3 sulfates. The 2 and the 3 in the formula are not reducible, and so you can't do anything with that formula, and that actually is the formula. The top one is the drug that they use for anemia. And the thing is, chemistry students might say that these 2 can't be that much different because all it is an extra line in the Roman numeral. It's got to be a chemistry teacher thing. Who really cares? Well, first of all, I want to tell you that these 2 compounds are definitely different because they have completely different chemical properties. I want to show you how much different these are. They're actually, iron 2 sulfate is green and iron 3 sulfate is yellow. So they're very definitely different compounds. The other thing is that if you have iron, iron 2 is the one that's in your hemoglobin that carries oxygen in the blood. If you convert one of those to iron 3, it's now a form of hemoglobin called methemoglobin, and it won't carry oxygen at all. If you had all of the iron in your body turned into iron 3 immediately, you would be dead within no time because you wouldn't be able to get any oxygen to your brain. So these are important differences, and I think a lot of the reason why people think that these differences are not that much is because they go by how it's written. One extra line can't really make any difference, but I want to show you that one little extra line can make a lot of difference. Now all I'm going to do in this word is just make one little extra line. A little line can't possibly make any difference, right? Well, there it is. I think it's just a slight little bit of difference. See, you already learned how to do this with language, and now you need to learn how to do it with science stuff, because the thing is, part of learning science is learning when are differences that are only written a little bit differently actually important, and recognizing how that is. Another example is that combination of IDE, ITE, and ATE. This compound is aluminum sulfide, and you can tell that the sulfide is the S2 minus because the IDE means a negative ion that is a monatomic ion with no oxygen attached. It's one of the ones that's on the periodic table that I showed you in the upper right-hand corner. When you cross these two numbers, you get Al2S3. Al2S3 is very toxic. If you take it into your stomach, it will release H2S gas, which is sewer gas, and that is poisonous, and probably if you eat enough, it would probably pretty easily kill you. But there's another compound called aluminum sulfate, which would have SO4 That is completely non-toxic, and it's actually one of the components of baking soda, which you can actually eat. So the difference between IDE and ATE could also be the difference between being a deadly chemical and something that's useful. The last one that I show here is got that mercury 1 ion in it. Mercury 1 is the ion that you can't reduce. It has to be written as Hg2, 2+. And so I put that in parentheses along with the phosphate here. And when you cross the 2 and the 3, you end up with that formula that's circled, and there's nothing you can do with this because mercury 1 phosphate that's what the formula is. It's 3 groups of Hg2. And so it just has to stay that way. Sometimes when you're doing a problem, you have to do the reverse, where you know what the formula is, but you don't know which charge the metal ion has. So I showed an example here of where you know that you're dealing with a compound that's chromium carbonate, but you don't know which charge the chromium has. And so you can do this algebraically, because you can make chromium equal to X, and then since there's 2 of them, that's 2X, and carbonate is a -2 ion, and there's 3 of those. And the whole thing has to add up to 0. So if you solve this for X, you find out that the chromium is actually the +3 ion, but there's an easier way to do it, which is the way you can usually do it. Since you brought the 3 down from the chromium onto the carbonate, you can kind of mentally uncross. You don't have to do this, but you can see very clearly then that the 3 is the one that would have come from chromium, so it's a +3. And the thing about that is you could also tell that the carbonate then was -2 if you forgot that charge. The other thing, there's only one problem with using uncrossing, and that is in the formula down at the bottom, manganese phosphate. If both of the subscripts are 1, they have often been reduced. And so that formula is the same as Mn1PO41, but if you uncross the 1, you would get a manganese 1, which there is no such thing. So since it's probably been reduced, all you have to do to get the metal charge in this case is, since you know that the phosphate is -3, the manganese has to be +3 in order to make it equal 0. So whatever the charge of the negative one is, the metal is the same except positive. This page is practice. You're not supposed to obviously memorize all these compounds. The idea is you're supposed to cover up the formula and look at the name, and you try to do the first one by crossing, uncover the answer, and see if it's correct. If you can get all of these formulas by crossing and you're correct, you can probably figure that you know just about how to do this very well. And at the bottom of the page, I give some practice ones for determining the charge of the metal ion if you know the formula. So you can either uncross, or you can use the idea that if it's 1 and 1, the positive ion has the same charge as the negative one except positive. The problems on these last 2 pages are actually assigned as homework problems in homework 1. And I also want to say that remember the 3 kinds of questions that I'm going to ask about naming on the test. I will give you an ion like Fe2+ and ask you for the name of it, or I'll give you the name of an ion like cuprous and I'll ask you for the formula of it, or I'll give you a complete name, aluminum phosphate, and I will ask you to write the correct formula by crossing. I will not go backwards, though, where you go from the formula of the compound back to the name, because that involves some trickiness and we don't really use it that much in class, so I'm not going to do it in that direction. This next part is that we want to talk about some of the things that you covered in 131 that we're going to recover in 132 in more detail. And the first one is acids, bases, and salts. I'm sure everybody remembers the definition that an acid makes H+ in water and a base makes OH in water. In an inorganic chemistry, you can identify the formula of an acid because it will have H written first in the formula. And the H will be combined with either a nonmetal or a polyatomic ion. If you look at those examples, HCl, of course, is hydrochloric acid, that's stomach acid. H2SO4 is got 2 H's in the front. We're going to talk about diprotic acids, but sulfuric acid can also be identified because it has H first. Now, as far as bases go, you can identify a base because it actually has OH in the formula. Anytime you take a metal, which would be positive, and combine it with the negative OH, you will get a base. If you look at the reaction at the bottom of this page, you know what neutralization is, where H+ from an acid reacts with OH from a base to make water, and that's neutral because water is neither acidic or basic. Whenever you mix an acid and a base, you always get as products a salt and water. And so I showed those. It depends on which acid and which base you use as to which salt you get. You can theoretically get any salt from mixing the correct acid and the correct base. That's why at the top of the page I defined what a salt is. A salt is probably over 90% of what we deal with in 132, because basically a salt is any ionic compound. There's only one restriction. The second ion cannot be OH, because if the second ion is OH, then a metal plus OH is a base. But any other ionic compound is considered to be a salt. Here's another classification that I want to talk about. When you dissolve a salt in water, we're going to find out that they are what are called electrolytes. When you take a compound like an acid, a base, or a salt and dissolve it in water, they form ions that are separated from each other. And because the ions are separated, the solution conducts electricity. That's why they're called electrolytes. What happens is, since the ions are separate, the positives can move towards the negative pole, the negatives move towards the positive, and you get conducting of electricity. That also means that there must be some compounds that are called non-electrolytes, which there are. And the main one is pure distilled water. Has to be, because that's the solvent. It's hard for people to believe that water does not conduct electricity, because you know how much of a shock you can get if electricity passes through tap water. The thing is that tap water is not pure. Tap water that comes from a faucet has all kinds of ions in it. And so the ions conduct electricity. If you get out all of the ions, either by distilling or deionizing the water will not conduct. That's the reason why in the lab, whenever you're doing an experiment, you always want to wash the glassware the last time with distilled water, because it takes off any of the ions from the tap water that could interfere with the experiment. Most of the organic compounds that are covalent are non-electrolytes. And the two that I want you to remember, because they always use these on standardized tests for things that don't make ions, is sugar and alcohol. Those are organic, covalent, but they don't make ions. And most other covalent compounds are also non-electrolytes, with just a few exceptions. I tried to draw a picture of what electrolytes are like. If you look at that picture at the top, in physics, you draw a battery by using long and short lines. So that's a battery. If the two electrodes are not touching, you won't get any current, because electricity has to travel in a complete circuit. But if you touch them, that's what a switch is like. You turn the switch on and the bulb lights up. Now, if you take the two electrons and put them into either pure water or a solution of sugar water or alcohol in water, you will not get any conducting, and that's why those are called non-electrolytes, because they do not produce ions, and so the solution does not conduct. At the bottom of this page, though, I showed that if you put in water either a soluble salt, a strong acid, or a strong base, you will get conducting. And those are what are called strong electrolytes. They produce a lot of current, just as if you had touched the two electrodes with a wire. At the top of the page, there is a kind of electrolyte called a weak electrolyte, and those are mainly weak acids, and also one weak base. Ammonia is considered a weak electrolyte. But the reason why these are weak is that weak acids do not produce very many ions. Strong ones give you 100% ions, but weak ones maybe give you only 1% or so. So you get a little bit of conducting, but not very much. And that's why the light bulb would be dimmer. We're not going to talk about weak electrolytes just yet, because we have to do weak acids in class first. But I do want to show you a picture of someone who did this in the lab. This person connected these light bulbs up to an actual electrical outlet system, and if you put the two electrodes in pure water, they don't conduct at all. But if you look at the hydrochloric acid in the lower right, it conducts electrons very well. HCl is, we're going to find out, is a strong acid, and so it gives you 100% ions. and that's a strong electrolyte. The acetic acid that's on the lower left is a weak acid. You notice that it's got one H in front, but there's three H's in the middle of the formula that don't come off in water. And I'm going to show you that more when we do weak acids. But the reason why that is a dim light is because you only get a few ions in a weak acid like that. That formula, C2H3O2, is the acetate ion. We're going to use that all throughout the whole semester in Chem 132 for different things. And a 5% solution of acetic acid in water is what's called vinegar. You can actually buy it in the grocery store. In the beginning of Chem 132, we actually discuss three main kinds of reactions. We talk about precipitations, acid-base and buffers, and redox. I want to introduce precipitation reactions today, and these are the first ones that you deal with in lab. The picture that's here is, we're doing the reaction at the top of the page. If you look at that equation, if you remember from 131, you were told that there are classified 5 different reaction types: combination or addition, decomposition, single and double displacement reactions, and combustion. If you look at the reaction at the top there, it is a double displacement because it's like the K and the lead trade places, and they get attached to the ion that the other one was attached to. This is also called a metathesis reaction because that word in Greek means trading partners. So the metals trade partners. The thing is, we ran that reaction in the lab, and the person doing this put a couple of drops of one of those solutions into the other, and you can see that it formed yellow stuff. The question is, how in the world can you form yellow stuff when you mix two clear solutions? Well, that's chemistry. If I was going to define chemistry, I always say you would take one kind of junk, you mix it with another kind of junk, and you get a third kind of junk that's not either one of the first two. That's what chemical change is. The yellow stuff that you see is actually the PbI2 solid that you see in the reaction as a product. PbI2 is an insoluble compound, and so it doesn't dissolve. Now, if you stirred that up, that beaker, the yellow stuff would disperse, but eventually, if you let it sit, it would fall to the bottom. And when it falls to the bottom, it's going down somewhat like rain or like snow. And that's the reason why they call the yellow stuff a precipitate, because it is going to the bottom. In the lab, if you want to separate a precipitate from a solution, you have to use a centrifuge. You put the two test tubes in, the centrifuge goes around very fast, and the centrifugal force makes the solid go to the bottom right away, and you can pour off the liquid. That is how we separate ions when we're doing qualitative analysis in the lab. You're going to be doing more quantitative experiments this semester, but we're going to do problems with precipitation because that's how ions are separated. What you would usually do is you would have some ions that were in the solution, and the stuff that you add would precipitate only some of them, but not all of them. And then when you centrifuge it, you pour off the liquid, you separated the ions that are in the precipitate from the ions that are in the solution. That's how you separate ions in the lab. In order to understand electrolytes and dissolving better, I want to talk about how the two types of compounds dissolve when you put them in water. What does a covalent compound do? if you try to dissolve it. I showed the C6H12O6, which you know is glucose or sugar, and you know that if you put sugar in water, it's going to dissolve, right? The thing is, what happens when that occurs? What happens is that water molecules pick up first a molecule of sugar, carry it away, and surround it. Then they reach into the crystal and do it again. By the time the whole crystal is gone, you end up with sugar molecules surrounded by water that are dissolved. Now the thing is, there are no charges here because covalent molecules are neutral. That's the reason why covalent substances do not conduct electricity when they dissolve in water, because they have no charge. The way I wrote this equation was just to change the solid to aqueous, because that's really all that happened. It just got surrounded by water. But if instead you dissolve an ionic solid in water, like sodium chloride, there are no molecules. The only thing it is alternating positive and negative ions. So the dissolving process is different. If you put salt in water, of course it's going to dissolve just like the sugar did, but something different happens. The water molecules, when they reach into the crystal, don't find any molecules, and therefore what they pick up and carry off are ions. After it picks up and carries off all of the ions, you end up with sodium ions surrounded by water and chloride ions surrounded by water. And they're now free to move. So if you put electrodes in, the positive goes towards the negative towards the positive, and the solution conducts electricity. You can write this as NaCl aqueous, but in our problems, we usually want to be more descriptive. We will usually write it as we did down at the bottom of this page, where you show that the sodium chloride solid actually splits apart into sodium ions, aqueous, and chloride ions, aqueous. Before the end of this class, I want to make sure that everybody knows how to write the dissolving equation for any ionic compound that I might give. So the first one we're going to do is calcium chloride. My first question is, how do you know this is ionic? Well, ionic compounds have a metal, and calcium is a metal, so it is ionic for sure. So since it's ionic, what is in the formula? Calcium chloride, because it's ions, will be made up of all ions, and so it's going to actually be a Ca2 plus and 2 Cl minuses that are separate. When that salt dissolves, all of the ions that are there split apart in water. So what you end up with are calcium ions surrounded by water and 2 Cl minuses surrounded by water. The thing is that I want to show you that there are two things that are very critical in writing this equation. And in order to do that, I want to show you the difference between using a subscript and a coefficient in a chemical reaction. If you look at the Cl2 that's in calcium chloride, it is completely different from if Cl2 is by itself without a metal. It's not the same at all, even though it's written the same way. When you put the 2 in front, it means something different. See, when you have the 2 as a subscript, it means that those two ions or atoms are crammed together somehow, either in a covalent molecule or in a crystal. In calcium chloride, it would be in a crystal. Cl2 is the element chlorine, and those two chlorines are connected by a covalent bond or shared electrons because there's no metal present. So that is the 2 in both of those is used as a subscript. When you put a 2 in front, like you do in front of the 2Cl-, it means that the two things are separate from each other. So if you want to show two Cl's apart from each other, you have to put the 2 in front. There are two things in a dissolving equation like this that are absolutely required. One of them is that it has to be balanced. You can't do anything without a balanced equation in chemistry. And so there has to be a 2 in front of the Cl-. The other absolute requirement is that you list the charges of the two ions. The reason why that's so important is I want to use as my example calcium ion. If you show a chemist the symbol of calcium without the 2+, the chemist thinks of calcium metal. Calcium is a shiny silver metal. You have to scrape the junk off that reacts with the air. It's got a coating outside in order to get it to react. Calcium metal is so reactive that if you put it in water, it actually gets very hot. It's exothermic and it releases hydrogen gas, so it starts to bubble. If you tried to eat a piece of calcium metal, it would burn you in your mouth and on the way down into your stomach. But when you put the 2+ on calcium, that means it has lost the 2 electrons that it wants to lose, the valence electrons. Calcium ions are perfectly harmless. Those are what you find in your bones and teeth as part of the structure. That's what you take as a calcium supplement when you're taking pills or drinking milk. Those are perfectly harmless because they've lost the 2 electrons. It's very important in chemistry to either put a charge or not, depending on which it is. This next one shows a different kind of an ion. Sulfate is polyatomic. So you know, though, that this is ionic because potassium is a metal. So what are the ions that are in it? When you have a polyatomic ion like this, the bond between the sulfur and the oxygen are actually covalent, not ionic. That's the reason why sulfate stays together as a group. But certainly the bond between the potassium and the sulfate is ionic, and so the ionic bond gets split apart in water, but the covalent one does not. So when this dissolves, you get what's on the next slide. You get 2 K+, but you keep the sulfate together. Covalent bonds don't get split very well by water. You notice it is balanced, and it does have the charges. The aqueous is kind of optional, because the only other way that you can get ions to split apart other than put them in water is to melt the crystal, and that requires such a high temperature that nobody ever does that in routine labs. So you can assume if the ions are split apart in this lab, they're aqueous. I want to do a couple more examples of these. If you, for example, dissolve aluminum nitrate in water, the first thing you're going to have to do is commit yourself to what are the two ions that are present. You keep the polyatomic ion together, and then the next thing you have to do is balance. After you put the 3 in front to balance the nitrate, you now need charges. Aluminum is in group 3, so it's +3. Nitrate is a memory ion, it's -1, and so you could also get the -1 by uncrossing the 1 from the aluminum up on the nitrate. In this one, though, when you're trying to dissolve iron sulfate, you know that you're going to split it apart into the iron and sulfate stays together. The problem is, which iron is it? Because iron can be 2 or 3. Now, you can balance without determining that, because you're going to have 2 irons and 3 sulfates. But now what about the charges? You can tell that this is iron 3 because you can uncross the 3 from the sulfate up onto the iron. So the iron is +3, the sulfate is -2, and that's a complete dissolving equation. In the bottom one, you have the ion ammonium together with carbonate. Ammonium is very common in ionic compounds, and so you use ammonium everything in the lab connected to a lot of things. When you dissolve a compound like ammonium carbonate, the polyatomic ions stay together. In balancing, then, you have to put a 2 in front of the ammonium, and ammonium is +1, carbonate is -2. So this is the correct dissolving equation. We already looked at the fact that if you dissolve an ionic compound like sodium chloride in water, you get the ions. The thing is, we have to talk about dissolving a little bit more, because what we want to do is, by the end of the class, we want to be able to look at double displacement precipitation reactions like the one that we showed with the yellow stuff forming in the test tube or in the beaker. We have to do those ionically because what's actually in the solution are ions. And in order to do that, we have to look a little bit more closely at dissolving. So the thing about it is, sodium chloride dissolves quite a bit. How much does it dissolve is the question. I looked it up in the Handbook of Chemistry and Physics, and it says that you can dissolve 357 grams of salt in a liter of water. A liter of water is 1,000 ml. Each ml weighs 1 gram, so the water would have a mass of 1,000 grams. You can dissolve over 1/3 as much salt as the water. This is a lot dissolves. When you have a salt that dissolves that much, chemists call these soluble salts. It's very easy to see that they dissolve. When you write the dissolving equation for a soluble salt, you use a one-way arrow, because under our conditions, we're never going to get to 357 grams of anything. Soluble salts are always going to be 100% ions under our conditions. Now, not all salts dissolve anywhere near to the same extent. The next slide shows silver chloride, which doesn't look that much different from sodium chloride. It's one metal with a Cl, but that salt only dissolves 0.002 grams per liter. That's only 2 milligrams, which is a very, very tiny amount. If you take a little pinch of silver chloride and put it in water and stir it, the solution just looks like milk, because you can't see any dissolving. Now everything dissolves a little bit, but you can't see it. When you have a salt that only dissolves a little bit like that, that's what chemists call insoluble. What that means is by eye, because everything dissolves a little. You can more accurately call it a sparingly soluble salt because it doesn't dissolve much. When you have an insoluble salt, you write the dissolving equation with an equilibrium arrow because it sets up an equilibrium right away when you just put in a little pinch. And so that's how you indicate an insoluble salt. Now the thing is, if I were a student, I would want to ask, first of all, is there anything in between? And the answer is very little. If you do it by eye, you can very easily classify most salts as either soluble or insoluble, although there are a few on the borderline, so you have to specify where the cutoff is. The other question I would want to ask is, how do I know which ones dissolve and which ones don't? Well, on the next page, I want to show you one way to do it, which is probably not the first choice, but you can use it. This is a table of all kinds of ions and compounds that have been tested. And you can see that the positive ions are across the top of the table and the negatives across the side. If you take the positive ion at the top and go down the column, and then you choose the negative ion from the left and go across, the place where they intersect tells you whether the compound between those two ions dissolves or not. If there's an S in the square, obviously it's soluble. If there's an I, it's insoluble. And there's only a few that are SS, which are actually compounds that were discovered by the German secret police. Now, that's not what they are. Anyway, they are slightly soluble ones. And the ones with dashes in the squares don't even exist in water. The thing is that you don't usually want to use this kind of an extensive table, but it is a good reference because you can use it in any class that involves salts. Earth science, geology, physiology, anything, anatomy, whatever. In chemistry, though, we determine whether something is soluble or not more commonly by using what are called solubility rules. I want you to know how to use 4 of these because these are the ones that we need for the whole rest of the class. You can find 15 or more of these things in an analytical chemistry book for every ion just about possible. We don't need that many. I just picked the 4 that we actually need and would use during the semester. And the first solubility rule is that any positive ion that is in group 1 of the periodic table will always dissolve. And this overrules any of the other rules we're going to talk about. So these are positive ions that make everything soluble. If you see one of them in a compound, the compound will dissolve. So all the ions from group 1 in the green box here make everything soluble. And so does NH4+, which is a +1 ion that's not a metal, but it acts like a metal in that case. So ammonium salts are also soluble. The second solubility rule concerns negative ions that make everything soluble. And there's 3 of them: chloride, nitrate, and acetate. So here's another case where the C2H3O2 negative comes in, acetate. Anything with these 3 ions in it will dissolve. Chloride, of course, comes from, you know about sodium chloride, makes sense. Nitrate is another one. A chemist knows that almost any metal nitrate that you put in water will allow that ion, the metal ion, to dissolve, and the same with acetate. The way these work, though, is that there's always exceptions, and there's 3 major exceptions to this rule. Silver chloride, lead chloride, and mercury 1 chloride are insoluble. And if you're doing analytical chemistry, these are important because these are all a group in the lab called analytical group 1. And you can precipitate all of them with chloride. The last 2 solubility rules concern negative ions that make everything insoluble. Most metal hydroxides or bases are insoluble. There's only a few exceptions. The ones that are from group 1 make everything soluble, so those work. And then there's 2 others, which you need to be familiar with for problems. Strontium hydroxide and barium hydroxide are also both soluble. All the rest of them are insoluble. I want to show you why strontium and barium hydroxide are important. The ions in green are the ones that are soluble hydroxides. Radium hydroxide is also soluble, but nobody's ever going to do that around here because it's radioactive and we don't have the facilities to handle radioactive chemicals. But barium and strontium hydroxide are common ones. The reason why I like to bring this up is if you look at the one above strontium, calcium hydroxide is actually insoluble. And so this is where the cutoff is. It's a good thing calcium hydroxide is insoluble because your bones and teeth both contain calcium, including hydroxide and the other two ions we're going to talk about now, calcium phosphate and carbonate. If your teeth dissolved in water, this would not be a good situation. So this is a pretty important cutoff. And as I just said, carbonate and phosphate are also two negative ions that make everything insoluble, with the exception of Rule 1 and ammonium, which is in Rule 1, because everything else that has those in them is insoluble. Where do you find carbonate besides your bones and teeth? This is the ion that you use to carry carbon dioxide back to your lungs to breathe it out. We're going to talk about that soon in the next class. And it's also a large part of the Earth's crust. It's in limestone and things. So carbonate is a really important ion. It's also the main buffer in your blood. Phosphate is certainly important. You never heard of a molecule called ATP, did you? It's only where you get all of your energy from. Phosphorylation is one of the main control mechanisms of enzymes in biochem, and it's also the backbone of DNA. A nucleotide is made of a base, a sugar, and phosphate, and the phosphates connect to make the backbone of DNA. So you'll see carbonate and phosphate a lot, and they make everything insoluble except Rule 1. I like this cartoon, so you have to see it. This is what would happen if hydroxide, carbonate, and phosphate were not insoluble. I'll bet you that you didn't even know that this is where they got boneless chicken. These are chickens where carbonate, hydroxide, and phosphate are soluble. This is the far side. You either get it or you don't. So here it is. Now this is the reaction that I showed earlier where you make the PbI2 solid, which is that yellow stuff in the beaker. I want to analyze now this reaction ionically because it leads into the next class. When you put Ki in water, you're not going to have any Ki molecules. You are going to have K plus and I minus. And the same is true of the other two compounds except PbI2, which is a solid. Now you wouldn't know that because I didn't give you a solubility rule for it, but it is in that chart of ions. If you look at the lead across the top and the I minus across the side, and the square where they meet has an I in it, and so it's insoluble. I drew the beakers that you would have if you were going to mix those two things. Ki exists as ions, and so does lead nitrate. PbNO3, why is that soluble? Because it contains NO3, which is one of the soluble negative ions. So the question is, what happens if you mix these? If you mix these two beakers, the K and the NO3 are not going to do anything because they both make everything soluble. KNO3 will not do anything except the K and the NO3 just float around watching the other reaction happen. But if the lead and the iodide run into each other, they will form that yellow compound PbI2. The way you describe that is by writing what's called a net ionic equation. The lead plus the two I minuses make PbI2. Net ionic equations also have to be balanced and have charges. The thing is, If you're writing the equation for a precipitation, because you're forming the solid, you're going to put the solid on the right and the ions that form it on the left. The other two ions, K and NO3, are called spectator ions because they just watch. They're not really doing anything. All of these reactions have spectators in them. Now the thing is, the reason they call it a net ionic equation comes from people's paycheck. If you talk about your gross pay, that means everything you should get, that is your total pay. Your net pay is what you get after they take out taxes and any of your deductions and things. That's what you actually take home. So it's your pay without taxes. The reason why they call this a net ionic equation is because it's an equation that's written without the spectators. Net ionic equations are supposed to show only what reacts, and spectator ions do not react. They're just present. There's another way to get the net ionic equation. If you take that original equation and split apart the ions, you're not going to split apart the PbI2 because it is a solid and it stays together, but you would get 2 Ks and 2 Is. You would get a lead and 2 nitrates, and on the other side, the KNO3 would be 2 Ks and 2 NO3s. Then you do the same thing you do in algebra. You can cross out the stuff that's the same on both sides. And if you look, we just crossed out the spectators, and we are left with the net ionic equation. This slide is supposed to show that the net ionic equation will not change if you just use a different spectator. There's a mistake in the textbook if you're following. There should be a 2 in front of the NAI. I just wanted to mention it. It's not that important. But what I'm trying to show is that if you replace the K with an Na, it doesn't matter. The net ionic is the same. You can replace the spectators without changing the net ionic equation. You're going to precipitate a carbonate in the lab in the first experiment you do. And the thing is, I wanted to show you that when we do qualitative analysis, the first precipitate that we make is barium carbonate. I want to show you, you can already write the precipitation reaction net ionic for barium carbonate. We don't even know what the experiment is. You don't even know what the spectators are, but it doesn't make any difference. If you know that you're going to get a precipitation reaction, you first just write what you're going to form on the right of the arrow because you're forming a solid. Then what would go on the other side? It's just the 2 ions that make it up. That's it. So when you combine 2 ions to make a precipitate, that's called a precipitation reaction. The way this looks in the lab is on the next slide. If you take an ion in a solution like barium and you add another solution that has carbonate in it, what happens is that you form the precipitate between those 2 ions. Both of the ones you had together will have spectators and possibly buffers and all kinds of other things, but we're not interested in that. We're only interested in the net ionic equation, what actually happens. The thing is, if you look at a dissolving equation, it's kind of the reverse, because you are taking the solid and starting with that, and then the solid breaks up into ions. So if you want to write a dissolving equation for barium carbonate, you would start with the solid on the left and break it apart into the ions. I used an equilibrium arrow because barium carbonate is an insoluble salt. The one-way arrow is for the precipitation is optional. You could use equilibrium also, but usually people do things to drive the precipitation to the right, so you get a complete precipitate, so you'll usually see a one-way arrow for those. The dissolving equation is done where you take some already formed barium carbonate. You can buy it from the chemical company or you can synthesize it yourself, and you put it in water and let it dissolve. These two kinds of problems are going to tie together the whole semester as we talk about precipitation, because we can do a whole series of problems where you take the two ions and mix them to form the solid. Those are called precipitations. Or you can take the already formed solid and try to dissolve it. Those are called dissolving problems. The thing about it is, because of the fact that these salts that you put in water are not soluble, you actually, if you want to dissolve them, have to put something in the water that will force them to dissolve. So precipitation equations are pretty easy to write. You just combine the ions, but dissolving equations are more complicated because it's going to be the solid plus something that you add that forces it to dissolve, even though it's insoluble in pure water. And so those are going to be more complicated equations, and you have to discuss each one individually. I showed pictures of the two kinds of reactions in another way at the bottom of the page. The precipitation occurs when you mix the two ions together to make the solid. The dissolving is when it dissolves to make the ions in solution. And if you want to completely dissolve the salt, as I said, the dissolving equation will look more complicated than what it does here because you have to add something to the solid to force it to dissolve. And now in the next class, we're going to talk about, because of the fact that dissolving equations are an equilibrium, we're going to talk about the equilibrium constant for the dissolving of insoluble salts.